This next series of problems deals with counting, and not counting 1, 2, 3, 4, 5, but doing counting where we're looking at something called permutations and combinations. We're not going to go through and develop that theory, but what I will be looking at is how to analyze these problems and solve these problems in a pretty reasonable way. This first problem says there are 6 people waiting at a bus stop. Luckily, there are 6 seats available on a bench. In how many different arrangements can these 6 people sit in those 6 seats? I think the easiest way to think about this problem is to think about the seats. 2, 3, 4, 5, 6. So I'm going to make a dash that represents each seat on that bus bench. And begin to think about it. If we just tried to take all of the people and find all the different arrangements, we would be here a really long time. So we're going to go about this a little bit more systematically and think, okay, I'm going to start with the first seat on the left and say, how many different people would it be possible for me to place in that seat? And we go, well, we've got 6 people. Any of the 6 could fit there. So there's 6 possibilities to fill that first seat. Now, once we have someone in that seat, the next question is, so how many people are left to sit in the second seat? Well, we've already used up 1. We had 6, so now we have 6 minus 1, or 5. So there are 5 people who can sit in that second seat. Go to the third seat. We've already got 2 people sitting. There's only 4 people left, so we have 4 choices of people to place in that seat. Then we'll have 3 in that seat, 2, and then finally at the end, once we have 5 people placed, there's just 1 left. And the number of possibilities, we're going to use the fundamental counting principle, is 6 times 5 times 4 times 3 times 2 times 1, which is a very large number. This next problem, Libby is in a race with 4 other people. In how many different ways can they finish first, second, and third? So this problem is very similar to the last problem that we looked at, but in this case, when we have 3 slots to fill, right? First, second, and third. There are fewer slots than there are people. So that's something to think about as you solve the problem. And in looking at this, we can solve it in exactly the same way. We have these 3 slots to fill. How many ways or how many different possibilities are there for the first slot? In this case, there are 4 other people, so there's a total of 5 people in this race. It's really tempting to start with the 4 because we've got 4 other people, but there's actually a total of 5. So there are 5 possibilities for the first place winner of the race. Then once the first place winner is decided, there are now 4 possibilities of people that could come in second. And then once we have first and second place decided, there are then 3 different people that could finish third. And so here, the total number of different ways will be 5 times 4 times 3, which is 60. In this next problem, we have Joe Torre, the American League All-Star manager, figuring out his batting order for his 9 starting players for the All-Star game. If the pitcher always bats last, how many different batting orders are possible? So this one, although similar to the other problems we've looked at, we actually have some more specific criteria for the order of the players. So we know we have 9, so we need 9 slots. 1, 2, 3, 4, 5, 6. But we do know that the pitcher always bats last. So the pitcher is here. So there's only 1 possibility for that last slot. Okay, and I'm going to place the pitcher first in this last slot. because it's not possible that the pitcher will end up in the other 8 slots. Okay, so now we can look at the other 8 slots. We don't have any other, what is the word I'm looking for? Restrictions, thank you. We have no other restrictions on the order. So we have 8 possibilities there. Remember, we've already used the pitcher, so there's only 8 players left. Then we'll have 7 in the second slot, 7 choices. 6, 5, 4, 3, 2, 1. So when we multiply all these together, we're multiplying 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 times 1. In this problem, the 5th grade class must elect 2 persons to the student council. 5 students are running for election. How many different pairs are possible to be selected from the 5 different students? So this is going to be similar in some respects to the problems that we've looked at previously, but it will have one important difference. All right, so we can start off just like we did before and say we've got 2 slots to fill. And for the first slot, there are 5 possible candidates. And for the second slot, there are 4. Now, we might want to say, all right, so now there are 20 possible pairs. But here's where it gets a little bit tricky, is that if we have Liz and Jeremy here, or Jeremy and Liz like this, that's really the same pair. Okay, so what we need to do is divide this 20 by 2 to eliminate those duplicates. All right, so every pair we have, there were 2 possible ways they could be listed in this scenario. So we're really looking at then 5 times 4 divided by 2, which is 10 different possible pairs. The next series of problems that we're going to look at are what we call the handshake problem. And this is a very famous problem that comes up in many guises and in many different ways. The basic premise is that you have a group of people that all shake hands with each other. And presumably, in most scenarios, they shake hands with each person one time. So this problem is very much like the one we just looked at with the student council elections, in the sense that we have 2 people shaking hands. So we're assuming we don't have a 3-way handshake. And so if we choose people to shake hands, there's 4 possibilities for the first person, and then there are 3 people left to choose. And so again, this looks like, well, maybe there are 12 handshakes that take place, but we need to beware of duplicates because Anna shaking hands with Bart is the same as Bart shaking hands with Anna. And that will be true of any pair of people shaking hands. We don't want to count them twice. So again, we're going to have to take this 4 times 3 and divide by 2. So 6 total handshakes take place. Another way to look at this, and this works with small numbers of people, is to draw a diagram and count it out. So if we have Anna, Bart, Carla, Dylan, we can say, okay, Anna shakes hands with Bart, Carla, so these kind of go together, right? These guys shake hands. Well, now Anna's done. Okay, we've got 3. Now Bart, we have to count him shaking hands with Carla, Dylan, and then finally Carla and Dylan. So we still get 1, 2, 3, 4, 5, 6 handshakes taking place. This is another variation on the handshake problem. But what is a little bit different about this problem is it's not asking for total number of handshakes. It's actually asking you to figure out how many times an individual shakes hands. So we're going to solve this in a slightly different way. So what I'm going to do is imagine I'm the one shaking hands. So I'm one of these 7 friends. So I'm going to shake, if I just shook everyone's hand once, 6 hands. So I have 6 hands I shake. So I shake 6 hands if I shake each person's once. But in this scenario, it's saying that we don't just shake hands once, we shake hands 3 times. So in that case, I would be shaking 6 times 3, or 18 total handshakes. So let's think about why, if we tried to solve it the way we've been solving these handshake problems, where might we go wrong? Because if we did it the other way, we'd go, all right, there are 7 times 6, right? So 7 times 6 divided by 2 is 21 total handshakes. But here's the subtle difference in this problem is we're not being asked about the total handshakes, but how many people shook hands. So we actually don't want to really be dividing by 2 here, because there were actually, if we look at that from the perspective of everyone involved, 42 handshakes were taking place, right? Because each of 7 people shook 6 hands. In this next problem, we can solve this using the counting techniques we've been developing thus far, or we could actually make a list because there aren't very many possible outcomes here. And I'm going to solve the problem both ways so you can get a sense of how this might go. Using the counting principles, we can say here's a penny, a nickel, and a dime. And just think, well, how many possibilities are there if we toss a penny? We could have heads or tails, right? So there's 2 possibilities. Same is true for a nickel. Same is true for a dime. So there's a total of 8 possibilities when we toss these 3 coins and look at the results, whether they're heads or tails. Another way to think about this, and this is a technique that's going to help us later, is looking at a tree diagram. One thing we can do is say, okay, so if this is our penny, it could be heads or tails. Then we can go, okay, so if it was heads, the nickel could be heads or tails. And if it were tails, it could be heads or tails. Whoops, that's not a very good T. Then, so this is our penny, this is our nickel, and then our dime. So for each of these possibilities, we could do heads or tails. For a total of, if we count out all our branches, 1, 2, 3, 4, 5, 6, 7, 8 different possibilities. You could also make an ordered list with the same kind of information.